Sweet.
Maybe set a title for it.
The title.
On the top.
Okay. All right. Let's start. So this is the repository that we're going to talk about. I think I just committed the latest take. And yeah, we're going to walk you through what we have built so far. Actually, we have built quite a few things that are quite complex, so not sure if we will get through everything. Also, we have not completed like the entire round trip yet. It's multiple stages of this challenge response sequence. We have implemented most of it, but not everything. And I'm not sure how much sense it makes to like go through it all. But we just see how it will evolve. And in general, we have not prepared much. We want to make this like interactive. I guess we can trust you guys that you won't DOS us. So just ask questions. And yeah, we're trying to make it an interactive thing. If you have any questions, just ask. Yeah, the most natural point to start would probably be the scripts. That is like the most low-level part, or like this is the thing that we where we build like the adapters to connect the bitvm to Bitcoin script essentially. And for that we have implemented a couple of interesting things. I think the first thing that I should show you is the interpreter, which is which is just a tool to run Bitcoin scripts. And yeah, you can go to this website. It's also online here on github.io something. Yeah, I think run. No, here. Yep. So it's also online here if you want to try it out yourself. Yeah, the first thing is that you just select a directory, and then in that directory, the files in there will be okay. like these files in here. The cool thing is when I save the file, it automatically gets executed. It should get executed. Ah, okay. Yeah. At least Blake works. So the cool thing here is I can edit a file, a script file, in my regular text editor. When I save it, that website recognizes it and immediately executes it. Here it just pushes true onto the stack because the entire script was true. But if we want to see like an intermediate result, we can do just debug here, and then we see the hash that was computed, and then it gets compared here to that hash. I think the endianness is a bit different. Where's the E7? Ah, yeah, E7, and so on. And yeah, what you can see here is already lots of high-level opcodes that we have developed. The only low-level opcode that is in regular Bitcoin script is optrue, and all the rest is stuff that we have built on top. And we have built like something similar to like a domain-specific language, like a templating language that allows us to formulate more complex Bitcoin scripts. Let's see some examples of how that looks like. Something simple is maybe, maybe I should explain that we built this U32 type. Bitcoin script natively supports 32-bit integers. However, it has like a super weird data type that is not really U32. It is, for example, it flows over into like 5 bytes when there's an overflow, instead of just computing the modulo to the power 32. And this type is super quirky, and that's why we invented our own type, which we call U32. And that behaves just like a regular 32-bit integer, and it does overflow, and also it is a bit easier for us to implement other operations such as XOR or rotations, because Bitcoin script doesn't have natively bitwise XOR, so we have to emulate it ourselves. And it's not straightforward because you essentially have to go through every bit, and the native type would not be very well suited for that. So we have this U32 type, and things are represented as 4 bytes on the stack. So when we push, maybe I should show you an example here. Let's just delete all of that. Let's make a new program. All programs are just arrays in our language. And if I do something like U32 push, and then I push some number, let's say 4042, then it pushes 4 bytes onto the stack. Here it's grouped. This is how the stack actually looks like. It's 4 items to represent a single U32. And then I can work with that. Like I can do U32 add, for example. Add takes 2 arguments. It takes the positions of, or like the addresses, the addresses of the 2 items that should get added together. So I add item 0 and item 1, which is this one and that one, of course. And then, I need commas. And then it gets added. And this is add without dropping. When you do this, then it drops the values that it consumes. Otherwise, I think the last value, this one, stays on the stack usually. And this is the basis for our high-level language that allows us to express other things. What's also cool here is that we can just add regular JavaScript here. Like what we write in here gets executed before it's compiled down to Bitcoin scripts. So we can do things here, like, for example, we build a loop function that takes as an argument the number of times that you want to loop, for example, 23 times. And then you have a function where you get an index, and then you have an output, and then I can do something like, for example, this would push this value 23 times, as you can see here. Or we can do maybe more interesting. Let's do 42 times I. And then you see that it pushes 42 times, and it is like a bit of static computation before that. And yeah, this is a very fundamental primitive because it allows us to unroll loops in a very handy way. Yeah, and also a very important thing is that we can build functions. For example, I can do a function, my function, and that can take like some parameter, my param, and then it returns a program again. And programs, as I said, they are usually just arrays. And then I can do some stuff here. For example, I could do, I don't know, u32 times my param or whatever. And then I can call it here to do my function 1 and my function 2. And then it pushes these two values. And this is essentially the foundation of it all that allows us to also nest functions. Like we could have a second function here and then like in the first function we call the second function, stuff like that. I think you get what I mean. The point here is that this way, like using JavaScript as a templating language to then compile Bitcoin scripts is a very powerful approach to tame the complexity of complex scripts. This way we can break it down into small units that are easy to implement, and then we can compose them into more complex things without going crazy. Yeah. Do you guys have any questions so far?
What's the most complicated thing you've built so far?
Good question. Oh, by the way, maybe I should show you the ASM file as well. Oops. Yeah, here it's super boring, of course, because it's only pushing values. There's nothing very spectacular in here, but I could use, for example, Blake 3 here, which also answers Super Testnet's question. This is the most complex thing we have built so far. Okay, it needs proper inputs, otherwise it fails. So maybe let's do something more simple at this point. Let's do u32 at 01, and then let's look at the ASM file, and then you can see this is the Bitcoin script that it compiled. And yeah, this is essentially the main idea behind this entire templating language. We can express things in JavaScript, and then it compiles down to this quirky language that is hard to understand. And yeah, Super Testnet asked what is the most complex thing that we have built so far, and it's definitely Blake 3. This is, yeah, as you can see here, it computes a Blake 3 hash, and the code of it is quite complex. Yeah, I think I will not go too much into the details. The heart of Blake 3 is this so-called quarter round. And here we implemented the quarter round function, and it takes, it uses mostly 3 operations, which is u32 add, u32 XOR, and then different kinds of rotation. This is a write rotation by 16 bits. That's a write rotation by 8 bits, by 12 bits, by 7 bits. And yeah, that is the so-called quarter round. And then per round, you do a couple of these quarter rounds. Where is it? Where do we call G? Yeah, here. This is a round, and this round calls the quarter round 8 times. And then the head function, what it does is that it does this round 7 times, and after each round, it does a permutation, which is implemented here. And here's maybe also a cool thing to mention, that this permutation function, it doesn't really do anything in Bitcoin script at the end of the day. It just, we have developed this little tool here that allows us to manage the memory and manage like to have identifiers to say, okay, here, this is my value A, and then we track it while it's moving on the stack. Because when I take elements from the stack, when I like I can, maybe I should explain how the stack works. The stack, we can put things on top of the stack, and we can take things from the top of the stack, and we can take things from everywhere in the stack, but we cannot push things everywhere in the stack. We can only push things on top of the stack. And when we take things from like the bottom of the stacks or so, then the rest of all the other positions change, of course. Like if I remove the lowest element in the stack, then all elements drop by 1. The positions of all elements drop by 1. And this little thing helps us to keep track of particular variables that are on the stack. So I can make a variable, call it like, let's say my variable A, and then I can just work with the stack and push elements and remove elements, and then I can just say anywhere in the code, hey, give me value A, and then it will look up the current position of value A and then return that. And this allows us to implement here this permutation function very efficiently. Where was the permutation? Here. Because it is just resorting the identifiers. It just relabels the values on the stack instead of actually permuting them. And that allows us to implement this compressed function, and the compressed function is essentially Blake 3. Here, this is just a bit of boilerplate around it to call it correctly. And maybe one thing I should also mention is our XOR table, because the implementation of XOR, we came up with a lot of interesting hacks to implement XOR in an efficient way. And it is using, like here, this lookup table. It has 256 elements, and we push this 256 elements onto the stack, and they allow us to compute XOR very quickly, like relatively quickly, without having to look into each bit. Like this XOR table works on bytes. Like I can put a byte in there, and then or essentially 2 bytes. Maybe shouldn't overcomplicate it here. Like it's essentially XOR for on byte level. And when I can do it on bytes, and I can also do it on 4 bytes, and then I have done it on U32. Yep. Any other questions?
So it looks like the heart of what you've made here is a high-level programming language that compiles stuff down to big honkin' Bitcoin scripts. Have you implemented bisection yet? And
yes.
if not, can you show us bisection?
Yeah. So all the things that I just showed here, this is just like our. Actually, it's not it's a bit more high-level language than Bitcoin script itself, but it's our low-level language. And then on top of that low-level language, we implemented a higher-level language that allows us to express more complicated transactions. And this is here, like this is at the heart of it. I think I shouldn't go too much into detail there, but what is important is in our world, we have sequences, transactions, and leaves. And essentially a sequence, for example, the bitvm sequence is a 3-dimensional array. So on the like we have an array, and that array consists of transactions. So here are lots of transactions in there. For example, 4 transactions. And a transaction is an array of leaf. And a leaf is, again, just an array. And in that array, there are Bitcoin scripts. Or like, there is one Bitcoin script. For us, a Bitcoin script is an array, as I told you before. So here on that level, there would be scripts, or this one script. And here, let's call this sequence, for example. This is my sequence, and then here there's a transaction. Oops. And then in the transaction, there are arbitrary many scripts, and each script is a leaf. So it would look like, this is essentially how our sequence look like. Many transactions, and then many leaves. And yeah, all the functions that we have just help us to build these kind of 3-dimensional arrays. And concretely, there's, for example, the bitvm sequence, which is at the heart of it all. Super Testnet asked is explicitly about the bisection process. Okay, how can I explain that in the most simple way?
You can show us the VM first, and then show us how it bisects afterward. If we're still interested, my mind might be too blown at that point to wonder.
Okay, yeah, this is our VM, and this is literally like a virtual machine that both the verifier and the prover they run that off chain, and that is the source of truth, basically the ground truth for both participants, for both players, as we call them. And yeah, here you can see the simple instruction set. We have not implemented too many different instructions yet. I think we haven't even implemented multiplication, but we have implemented addition, subtraction, branch if equal, and branch if not equal, and jumps. And yeah, like this is a very basic VM. It's the most basic VM that we could come up with. In the end version, it will be way more complex. We will have way more different instructions, but for now, this is all. And the interesting thing about it is that we can Merkleize the memory, and that allows us to create what we call a snapshot of the VM at every step. And this way, yeah, we can compute a Merkle root of the memory, and that is essentially the fingerprint of the snapshot. So at every step of the VM, we can have, or like we can compute the current Merkle root that is the commitment to the full state of the VM. And then there is a trace. Trace is essentially just the list of all roots. And what we are doing in our bisection process is that we are bisecting, or we are doing binary search over this list of roots. And yeah, this is essentially it. We are doing binary search over the trace, which is a list of state roots, or a list of Merkle roots of the memory. And what we are trying to find in that binary search is we are trying to find like a pair, which is root A, root B. And what we want is first, whoops, I didn't want that. First of all, the first property is they should be next to each other. So essentially root A dot index equals root B dot index, like here +1 equals root B dot index, if that makes sense. So they should be siblings, they should be next to each other actually. And the next property is root A is correct. Correct means we got the same result. Like, let's say we are the verifier and the prover made a claim. Then what we want to find is them committing to a root that we think is correct, that is the same value that we had, and root B is incorrect. So we are trying to find exactly the state transition from root A to root B, where A is correct and B is incorrect. That has the advantage that we know exactly the state of the memory at root A. So whatever they tell us about the state of the memory, if they say, hey, some value X is at address Y in root A, then we can look it up on our local machine if that's the truth or not. For root B, we cannot do that because root B is just, it's incorrect and we have no idea where it is incorrect. But we will figure out where it is incorrect. So yeah, exactly. We are trying to find this pair. This is the goal of our bisection process. And it's surprisingly simple. It's quite complex to get why it works, but the code itself is surprisingly simple because it doesn't do much. Maybe I should also explain quickly that we have another type, the U160, which is just, it's 160 bits, so it's 20 bytes, and it's just another data type that we have. And what's happening here is the trace challenge is just the verifier say, like, actually, it starts with a response. The first thing is the prover commits to their last state, to what they think is the final state of the VM. That is the first thing that the prover says. And then the verifier, they just release one bit. Like the prover releases 160 bits, or like they commit to 160 bits, which is their trace response. It's a 160-bit commitment. I'm not sure if that makes sense to you, like we have bit commitments. Maybe I should talk more about bit commitments and then talk about like what a 8-bit commitment is and a 32-bit commitment, just to make that really clear, so I don't lose you here. Let's look into these examples. I think here's some is a good one. Here is something weird. I don't know where it comes from. Okay, yeah, I see. We haven't used these examples in a while, and we just refactored the player, and now it's all a bit messy. Yeah, I will just show you the code. U32 state. So yeah, this is a bit state. This is very similar to what's in the white paper. It just has two hashes. Essentially hash 1 and hash 0, and you can unlock it by revealing one of those, and this way you set the value of this bit state. And we can do the same with 2 bits. So in this thing we can reveal 2 bits, and we use that to create also an 8-bit commitment. Like this way you can commit to 8 bits at once. Of course, it grows quite quickly and it's quite expensive because already a bit commitment has like 2 hashes and you need a pre-image to unlock it. So there's roughly 20 bytes plus the pre-image is roughly 60 bytes per bit, which is expensive, of course. But we can just put them together and then we have an 8-bit commitment, like a byte commitment. And that is then, of course, 8 times 60 bytes. But we can just keep on composing that and also build a U32 state. Then we have 4 8-bit commitments, which is 32 bits in total. And of course, it grows quite quickly, but it just works. And this way, we can define high-level variables in our scripts. I can just make a variable called my variable A, and that is a 32-bit variable, and I can just use it anywhere in my scripts, and I can use it amongst different in many different scripts and many different leaves, and everywhere will be the same value, or the person that commits to that value has to equivocate, which allows us to slash them. Okay, and
it's a program that you've written in the bits of assembly that you've coded up, like an addition program or something, and show us it working.
Sorry.
Earlier, I saw that it looked like you had coded up some assembly for this. You had coded up jump, you'd coded up branch if equal, branch if not equal, other things. Have you written any programs using those assembly commands and then run them through your virtual machine?
Yes, of course. For example, here's our dummy program. It's very, very simple. It just uses 2 instructions, and what it does is it adds, it takes the value in register 0 and register 1, and then adds them together and puts the result into register 0. And then it looks into register 0 and compares it to the value in register 2. And if that's not equal, then it jumps back to the first one. So essentially, it adds the value in register 0.
Yeah, it's like a for loop. It's saying add this until it's equal to whenever we're supposed to stop, and then go to the next step.
Yeah. Yeah.
Can you show it working?
Oh yeah, of course. It's a bit more complicated to start it now.
Because you have the premium verifier.
Yeah, like we kind of we destroyed the way to prove it to use it without starting the entire program. Like it would be better to have a couple more endpoints that would allow us to execute only the VM. But we have already assembled everything, and now it's harder to do only that thing than just doing everything at once. I'll charge quickly the contract. Okay, and then we have to start Paul, and we have to start Vicky. And then she started. And now we can look into Vicky. And Vicky has a VM. And in that VM, there's the program. And we can call vicky.vm.run. And if we call it without any parameters, it runs it until the end. And then it gives us that looks weird. Should have counted up to 10, I think. But long story short, what it does, it is, I think you have to trust me here. It just runs the VM, and we can also run the VM only until a particular step. For example, I could run it until step 3 or run it until step 4. You see the program counter changed, and the total step count changes. So, but this is only the VM that is run locally. And the more interesting part is to do that bisection process, actually. And when we run the VM, we get such a snapshot. And the snapshot can give us a root, I think. Yeah, exactly. That gives us the root of the memory. And what they are doing here currently is they are exchanging transactions. They are putting them on chain already. You can see here executing trace challenge leaf and On the other hand, you see it's executing trace response leaves. So they keep reading each other's challenges and responses, and then they respond to that. And how they are doing it is here, the trace sequence. Yeah, here in the logging script.
I have a question though. Shouldn't they only do a challenge and response if there was a dispute?
Oh yeah, of course. For testing purposes, we just simplified that step here, and we always have a dispute, basically. Like it always starts with, okay, they know they have a dispute, and now the challenge starts. It's somewhat a trivial step to add the question if there's actually a dispute or not. And it would be annoying for us for testing to always have that up front. Because this way we can also test if when they agree, then they should go through the entire sequence and always agree, right? And this is actually the case that we usually test. Because otherwise it will fail at some earlier point and then we won't get to the end. So yeah, it's good to start the challenge.
If there's a dispute, then Vicky and Paul must have different state roots, or does she challenge him anyway, even though they have the same state root?
No, if they have the same end state root, then Vicky would lose if she would challenge Paul.
So in your thing where she automatically challenges, does that mean she automatically has a different state root?
No. Here in this, like in this state currently, we just configured it for testing, and here they have the same root. But this just leads them to the conclusion to challenge like the last state. Like they will just agree on everything until the last state, and then they challenge the last state. This is kind of like this is not, it doesn't make much sense in practice. It only makes sense for testing. If that makes sense.
Yeah, I get that. I was just trying to work my head around what the test is doing.
Mm-hmm.
Cool.
Yeah, and then
so I saw something that looked like a program counter, and then I saw something that looked like a step counter. And my virtual machine also has those. And every time, what I think you're calling the step counter, mine has a new it's one clock cycle that goes by per step, and then 4 steps increments the program counter. It looked like yours also had 4 steps to increment the program counter.
Nope. The program counter is like steps is really the number of instructions that were executed, and the program counter is essentially the index of the next instruction that will be executed. And the program, for example, here, our program has only 2 instructions, but it could run for 1 million steps. If I put 1 million here, then it would run for 1 million steps, but the program counter will always oscillate between 0 and 1, because those are the only instructions that it can execute. So the program counter just tells you which.
So the step counter. What does the step counter refer to? Is it one of these? Is it the number 1 million or the number 10?
Yeah, it would be like the current, like for how many steps has the VM ran.
I see. And for every new memory state, how many? In my virtual machine, there are like 1,700 tap leaves, each encoding 1 logic gate, and then after 1,700, you have a new state of memory. So how many transactions would have to be done, or not transact? How many tap leaves are there between 2 different states of memory for your virtual machine?
This here works very differently. You could execute that program, and you can execute it for up to 4 billion steps, and then you have a trace of up to length 4 billion, and then you do this bisection game over that trace, and then you try to find this pair of roots where like one root is correct and then the other root is incorrect. And that is only the first step of it all. Once we have found this pair, then we will do the next step of the computation, which is actually, this is here where Paul has to commit to all the values of the current instruction, which is the current program counter, the next program counter, the type of the current instruction, the address that the current instruction is using, the value, or like the address A, value A, address B, value B, address C, and value C. That is a bit different than in your design. Here, all our operators always take values A, B, and C, and it's always A operator B equals C.
So the operator is, so I would expect there to be 4 values then. If you have A something B equals C, then I would expect there to be one somewhere for you to indicate which operation you're doing.
That's the instruction type.
Okay, that's the instruction type. I see. So that'll be add, subtract, multiply, or some others as you make them.
Those are the instructions that we currently have.
Okay, gotcha. So then, so how many? So you earlier you said you can have the thing run for 1 million. You change the number from 10 to 1 million. When you make that change, does it increase the number of tap leaves in your challenge address?
No, not at all.
Okay. So what increases when you in terms of Bitcoin? What increases when whatever increases the number of tap leaves in one of these transactions?
Nothing. We always assume that the trace has 4 billion steps. We kind of have like pseudo steps. If your program terminates earlier, then all the remaining steps will be just a copy of the last step. But it's easier.
Okay, I see. Yeah, that's like one of that's familiar to me because I made my virtual machine. I made a version of it that runs for 64 cycles, and then you always have the same number of steps, even if your program is smaller. So I see what you're doing there. That's similar to something I've done. So yours always runs for 4 billion steps.
To make stuff constant size, like our memory is constant size and the trace is constant size. The trace is always 2 to the power of 32, and also the memory also always has 2 to the power of 32 many cells.
Cool. So the remaining next steps, it sounds like, are to make more instructions and more example programs that can run in this thing.
Yeah, like I mean, like we have not done any computation yet, right? Like this is just a commitment. This is just Paul committing to all the values that he thinks are right. And then Vicky looks at these values and then tries to disprove them. Or like she knows that one of these values has to be incorrect because Paul's final state was incorrect. So something has to be incorrect. And yeah, she looks at these values and then she can react on what value was incorrect. And yeah, we have lots of different ways. For example, the instruction could have been executed incorrectly. So for example, it was right that we should have executed an addition here, and the addresses that they used, they are also correct. So they added the correct values. However, they got to the incorrect result. So value C is incorrect. And you could disprove that, for example, with this execute add leave, which essentially says, like Vicky takes some of the values that Paul committed to here and proves that they don't match. So she takes the instruction type and first she proves that this was actually an add, because she may not execute the add leave if the instruction was not an add. Of course, if the instruction was a subtraction, then the result will not be the result of an addition. That's why the first thing we have to check is that the instruction was actually an addition. Then yeah, she puts the value A on the stack, she puts the value B on the stack, she puts the value C on the stack, and then she adds A and B, and then she compares it to value C. Or like she proves that it is not equal to value C. And this way she disproved the addition. Does that make sense?
Yeah, I think this is kind of the same thing that Super did in his implementation for gates. So basically, a kind of same script exists in his implementation for basically invalidating a gate, or the way you did it here, like with the not equal.
Mine's only 8 bits and his is 32, so his is way better.
Yeah, and also like a bit like higher level, like higher level functions like add and subtract.
And also cool. Can push values. I think that was very helpful for us. That we got to the point that we can just push values on the stack, and we don't care at all that there is lots of complexity behind this with like the bit commitments that are actually pushed here onto the stack. We just abstract all of that away at this point. And the other cool thing is when we execute this, it's over. Like this already proves that Paul lied. If Vicky can execute this, then that is already, it's over. Vicky disproved Paul. And we have
make it happen, because then she gets Paul's money.
Yeah, exactly. So this is an end leaf, like it's a final leaf. And we have these kinds of leaves for every instruction. Here is another instruction. It looks essentially the same, just that here is subtraction instead of addition. Like we check that this is actually subtraction. Then here we use subtraction instead of addition, and that's it. The rest is exactly the same as in the addition leaf. Maybe a bit more interesting is the jump leaf, because it does something more interesting. Because what does it do here? The instruction, the jump is a unary instruction. It doesn't have 3 values. It has only 1 value. This is the address that it should jump to. Oh wait. It's actually correct. So what it does, jump, the first value of jump is the program counter, is the value that it should set the program counter to. So what it's doing here is first it proves that this was actually a jump instruction, and then the next thing is it puts the next program counter on the stack, it puts the value A on the stack, and then it proves, value A is not the same as the program counter that Paul claimed, which means he executed the jump leaf incorrectly. Maybe it gets more clear here in the branch if equal. That is maybe a bit more clear. Same as always. Proof that we actually execute the right instruction here. Put the program counter, the next program counter on the stack. Push the current program counter on the stack. Then push value A, B, and C on the stack, and then it compares A to B, and if they are equal, then it should jump. Otherwise, it should not jump. I don't know if I should go too much into detail why this is true, but this essentially computes the correct the next program counter, and then at the end it just compares the correct program counter to the program counter that Paul committed to, and it proves that it's not equal, which means he did not compute he did not compute correctly the branch if equal operation or instruction. Is that making sense? Like I'm so deep into the weeds that I have no idea if it makes any sense at all to you guys or not.
Part of it is that Go ahead, Technics.
Yeah, it all. I was just saying that it all makes sense, at least for me, that I have like read Super's implementation a bit, but I understand why it could be hard to understand for maybe other people.
If anybody here has any questions, just ask. Like, there are no stupid questions. It's just stupid to not ask if you have a question.
Yeah. Do you think every instruction type can fit in the stack?
Sorry, if?
Do you think every instruction type you're planning to add will fit inside the stack? Because I was expecting to do the bisection at this final instruction execution step, but I think you're not doing any bisection. Verify just disproves the instruction, right?
Yeah, I mean, you can always trade number of total transactions for size, or like total size that you need in the worst case, or like a total on-chain space that you need in the worst case. If you have more transactions, then you will get away with less on-chain space, and if you are willing to pay for more on-chain space, then you will get away with less transactions. And here we tried just to do some trade-off that we say it is fine to execute a leaf that is 5 to 10 kilobytes or so. That is, in practice, it might turn out to be a bit too large, so we should optimize it or so. But just to keep it simple, we assumed that it's okay to execute a leaf that has 5 kilobytes. And that's why we don't do it by this.
Yeah, that makes sense.
So it looks like you've designed a couple of intermediate representations before it finally gets down to Bitcoin script, and it looks like where you're currently at is you're designing assembly instructions so that you can write programs in assembly. Is that correct? Yeah.
I mean, the end goal is really to compile like Rust code, existing Rust code. Like, for example, we take an existing Rust verifier, ZKP verifier written in Rust that other people use in production for whatever projects. We use exactly that code, and then we compile it down to this. This is the end goal.
Yeah. In order to do that, you'll need to you'll need your what's it called? Your virtual machine to have the same instruction set that the Rust compiler can target.
Yeah, you can compile Rust with LLVM, and LLVM is very flexible, and it's probably not very hard to design an instruction set that is compatible with LLVM.
Well, it would be really hard for me, but I'm glad you're doing it because it sounds easy for you.
I mean, like, LLVM is kind of like designed for that. That's what I mean with it. Like, it's not a crazy idea that nobody has done before. It's more or less straightforward, and many people have done it. It's not like
you always go with the RISC-V route, get something very similar. So we don't need to kind of like write.
Sorry,
we can always go for using the RISC-V instruction set, of course, as well, because then we don't need to kind of write our own backend. So usually that's the end goal that we end up with here.
Yeah, actually, that is what we are aiming for, to add the RISC-V instruction set here. The only there's a difference, because regular CPUs work differently than what we are doing here. For example, regular CPUs usually have registers and memory. What we have here is only memory, and there is no inefficiency here. Like, regular CPUs, they have to deal with physics of how the CPU is architected, and we don't have to do that here, and that allows us to do things a bit more efficiently in some ways. So it wouldn't quite fit to just take RISC-V as it is and to implement it. Yeah, because a lot of instructions we just don't need. We don't need to load things from memory into registers or something. That is just
or you can make them into aliases essentially instead, because there's no reason why registers can't be memory mapped. So basically, you can kind of convert, let's say, instruction that goes in a particular registry into essentially, let's say, decoding it into something that just basically reads from memory instead.
That's a good point. Yeah.
Yeah, you could just define the last byte or the last memory register as register A, for example.
Yeah, my point is just you don't have to do that. Like you can do it, but it's just unnecessary steps. Like you can immediately read from any point in the memory, from any address in the memory without having to load it in the register first. Of course, you can build like an artificial register and then load things into it. But yeah, it's just inefficient. There's no advantage in doing that.
Well, I guess the advantage would be then you have load A and load B, so you don't have to modify the RISC-V architecture.
Of course, yeah. I just meant like there is no advantage on like computational wise. We cannot compute more things. It's not getting more expressive if we have registers.
Right. Yeah. So you said you think in 3 you'll have the RISC-V instruction set architecture ready on this thing?
Maybe by the end of the year.
Okay, end of the year. So that's a couple of weeks then.
Yeah.
Cool. So Linux on Bitcoin by end of year.
Yeah.
Sweet.
Okay, Lucas is just a great movie.
Robin Linus instruction set, yeah.
And Doom a couple of days later.
And I honestly don't think we need all the RISC-V instructions to be compatible with LLVM.
But I have to look it up. But I don't think so either. Like I think we can just modify some backend that exists already. Like not all the, but like many of the zkVM people, they are doing something very similar. That they are building their own VM that is very different than physical machines, and then they are customizing LLVM to compile high-level programs to their VM. And I think that's something other people have done before, and it's not too complicated because LLVM is more or less designed for that, or designed to also support that.
May I ask a question on bisection?
Sure.
Could you please like maybe expand a bit on what is actually happening in it, because I'm having a hard time, to be honest, understanding it. Like to me,
I did a lot of hand waving here, and I actually didn't explain really how the bisection works in detail. So.
Yeah, like to me, it's kind of hard to understand that because it's like a binary search, but I don't get it. Like, where do you actually decide on like jumping right or left for the sequences? Is what you calling it? Yeah, in the trace. Could you like maybe expand on it or explain on it a bit? Yeah.
Of course. So what's very interesting here is that this is extremely simple. It's just a sequence of verifier and prover taking turns, Vicky and Paul taking turns, and Vicky, she publishes a single bit, and Paul publishes 160 bit with every response. And then they take turns, 1 bit, 160 bit, 1 bit, 160, 1 bit, 160. And the 160 bits, they are always a memory root, just as I computed it here. I think here, such roots at different points. And in general, Paul could reveal whatever he wanted to. Like, there is nothing that forces him to do something particular here. But it's still, at the end, we can put it all together, because the interesting thing here, the bits that Vicky is releasing, they correspond to particular indexes in the trace. For example, like, yeah, if you take the bits and then you add them together, they make up the index of the last hash that Paul revealed. Or like, at least Vicky says that is the index of the hash that I want you to release. And what hash Paul releases is or like what hash Paul commits to is not how do you say I think I should show you just how to compute this index here. It should be up there somewhere. Oh, here, for example, this is the trace index, which is it's really the index of the last root that Paul releases. For example, let's say the trace has a length of 1 million or something, and then the last correct root was root, let's say 2000 or something, and then trace index will be equal to 2000 at the end. And why is that? Well, it is because at every point, like at every of her transactions in the sequence, she releases a single bit. And if you compute them together, like if you do like the bit value times 2 to the power of here the current index, then you get in total a 32-bit value that is exactly the index of the last root that Paul released. And this then is the same yeah. It's so subtle that it's hard to explain why it works in the end. Actually, maybe I have not understood it myself well enough. Otherwise, I could have explained it properly. But the interesting thing is, like, for example, here we are using. No, I should explain this first. Here, Paul makes a commitment and says, "Okay, those are all the things that I believe are true at the step that we ended up after the bisection process." And he just makes a claim. Like, he's not obligated to say anything that is true here. He just makes a claim. And for example, he claims that in the memory at address A there is value A. He says in the state root, the memory that hashes to this state root, in that memory at the position address A, there is value A. And Vicky knows exactly how the memory looks like, so she can see if Paul lied here. Like if Paul says the value is 42, but actually it's 23, then she knows it, and then she knows value A is wrong. And what she does then is she says, "Hey, well, okay, then I will ask you now to prove to me that you know a Merkle inclusion proof for this value A." Because she knows he cannot give you that Merkle proof, because she knows exactly what the memory is that hashes to the root that he revealed, to the correct root that he revealed. So she just challenges him to now reveal a Merkle path that proves inclusion for value A, which will be impossible because she knows that at address A there is the value 23, but Paul claimed that it would be 42. And she does that by not executing any of these leaves, because it's not about it's about the question if the instruction was executed correctly. The problem here is the value is incorrect. So even if the instruction was executed correctly, it doesn't matter because the values are wrong. So she's saying, I'm not going to challenge the execution of the transaction. I'm going to challenge here the value itself. This would be here in the root. There would be for her the ways to challenge the execution, but she's not doing that. She's saying, hey, I want to challenge value A, or I'm going to challenge value B, or I'm going to challenge the value of C. And if she is doing that, then she is opening up the next sequence, which is the so-called Merkle sequence. And the Merkle sequence allows you to disprove a Merkle path. And it's essentially the same again, that it is doing another binary search where they take turns. Paul, the prover, he releases, he releases hashes, intermediate hashes of the path, of the Merkle path. And Vicky, again, she says after every node that Paul released, she says, yeah, there was a correct node or an incorrect node, which forces Paul to jump up or down. And the fun thing here is that there is still no connection to the first challenge response process. Only here at the end, for example, here, if that thing actually ends such that she hashes such that he hashes such that he would end up with the root, but the root is incorrect, then Vicky can say, hey, okay, give me the root that you just created, which is her last Merkle response, and then she compares it to the trace response, to the last trace response. This is the first time where it actually gets connected. Everything else is completely disconnected, and Paul could lie how much he wants. Like, he can claim total nonsense. He can reveal every time the zero hash, for example. But it wouldn't matter, because at some point they would get to this point, and then Vicky could say, hey, I know this trace response, it was correct because we did the trace response such that the last one was the correct one, or like there was no correct one. That is another edge case. But if there's any correct root in the trace, then this will be the correct one. And then she compares it to what Paul computed as the Merkle root, and then she says, hey, those are not equal. And this way you get this, for the first time, you get a connection between the trace and the values in the memory. This was a super weird rundown, I know. I would not have understood it, but if you have more questions now, or like more specific questions to help me.
Yeah, but could you maybe like go back to where you said that then Wiki would decide go up or down? How's like?
That is here.
Yeah.
Here she releases a Merkle challenge, which is a single bit.
And then how does she decide to go up? Like what has to happen for her to like go up, for example?
Yeah, like the path has 32 nodes. Yeah, it's the entire Merkle tree has size 2 to the power of 32. So,
yep.
Or like the memory has 2 to the power of 32 memory cells. So the Merkle tree has 2 to the power of 32 many leaves, and that means any inclusion proof has 32 nodes. And what's very important is that both Vicky and Paul, they know the correct path. So Vicky knows which is the correct path. And then she asks Paul to reveal the node in the middle of the path. And then she looks at the node and compares it to what she knows is the correct path. And if it's the correct path, then she says 1. And if it's the incorrect path, then she says 0.
And that single bit would let people know to decide how to like basically move in this path.
Yeah.
Okay.
Because
I kind of get it, but I have to like think more on it.
Yeah, man, don't worry. Like, it took me quite a while to wrap my head around this. I don't expect others to like get it right away. I'm definitely not at the point where it's easy for me to explain it, and I'm pretty certain it's not easy to understand it.
A quick question, just maybe like not on the specifics of the implementation, and thanks so much for explaining this. The bisection protocol itself, is this something that you had to customize for this, or is this based on one of the existing? Because it's like bisection itself has been used before, like in TrueBit and Arbitrum uses this. Is there any like pseudocode or like high level algorithm somewhere that you've used for this, or did you have to customize one of them to work with bitvm?
I just came up with it.
All right. Okay. So you don't know if it's different or the same to what they're doing on TrueBit or Arbitrum, where they essentially do kind of something in that direction, right? So they kind of do you execute off chain and you play this game until you find exactly where the instruction is actually wrong.
Yeah.
Okay. I mean, I guess for people who want to and maybe it's not the same, but it's similar, and there's like the TrueBit paper and the Arbitrum paper have sections where they explain how the bisection works, or they reference something. So that might be useful if you want to just wrap your head around, maybe not the same exact implementation, but the idea of like how it would work in principle.
Yeah, we will definitely also write a paper about it, but we didn't know what to build, right? We are trying to find out what we should build, and that's why. That's actually the main purpose of the current implementation. We use JavaScript, even though we know JavaScript is it would be absolutely reckless to use it in production for anything real value. But it's super great to explore things and to figure out how things should be built. And once we get to a point where we are certain that this works, then we will also try to write a paper about it and explain it in better terms with diagrams and stuff.
Question. I mean, I guess any user, any node on the network that has this data, like any node basically could run the computation themselves and follow this bisection challenge and response game that Paul and Vicky are playing, and they would actually know exactly whether Vicky is on the right path, right? Because they would also be able to just run this binary search locally, and as Paul kind of progresses, so everybody would see it in public that Paul is essentially doing something right or wrong.
Yeah.
Does prover reveals the inputs in the first step?
No. I guess what you're referring to is this, right? The commit instruction leaf. This is where they reveal the inputs. And here you can see the sequence. Where is it? Ah, yeah, here. It's the kickoff transaction. Then we have the trace sequence. Then it commits to the instruction. Then it can challenge the instruction. And then it can use the Merkle sequence, but it doesn't have to. This is the entire bitvm sequence. And this is the step where it commits to all these values. So the commit just here, the commit instruction route.
Robin, did you manage to record this session actually, even though it's in Telegram?
I hope so. Yeah, it's still recording. Yes.
Oh, nice, amazing.
One question: If the prover doesn't give the inputs, the verifier should challenge the inputs to get the inputs, or is it a binary session?
Yeah. This is still very simplified. Here, dummy program, it's super stupid. The data is just known, and it's pretty pointless in practice. In practice, you will have to agree on some kind of initial configuration, and it might be necessary to also challenge the prover to reveal what they believe is the initial configuration. And also, it's probably like some have some kind of instruction that allows us to push data into the memory from after the initial setup. Like you could have an instruction that just allows either Paul or Vicky to set the value of a particular memory cell.
I see.
How does the cost, that's just like one transaction, how does the cost increase with that? Just thinking about like, okay, for a two-way peg, right, where you want to like verify whether, like there's a high chance that there's a dispute on what the inputs are, right? So that Paul saw a fork, for example, or Paul saw like something and he's claiming to have seen some data on a fork. So Paul produces a fork locally of the sidechain, for example, and then you kind of have to, but it's not deep enough. Let's assume he's able to kind of really break the model of this. How many transactions? Like, do you really have to run bisection on this as well, or do you just like, let's say Paul and Vicky realize, oh wait, Paul is like making it like the inputs are different. Like it just doesn't make sense. What next? Do you then challenge that basically? Do you then challenge, like, just then you basically don't even go to the execution step, but you try to figure out why Paul even, like, how that you basically challenge that Paul ran this on wrong data, or how would you challenge it?
Yeah, it's probably not possible to just have entire blocks or something. Like, for example, you could say, hey, on the sidechain, there happened 500 blocks and they all have like 10 megabytes. And now we have 5 gigabytes of data that we would have to feed into our bitvm. And that is not possible because in the worst case, the entire 5 gigabytes would have to get revealed on chain. And that is just not practical. So in practice, what we will do is we will use compression with zero knowledge proofs. So you will not challenge 100 sidechain blocks. You will only challenge a very compact proof. And in the worst case, the prover has to write the entire proof on chain, but it will be like, I don't know, maybe 20 kilobytes or something. I don't know how big is the Plonky 2 proof?
100 kilobytes?
Maybe 100 kilobytes, yeah. Then you would have to write maybe 100 kilobytes into the chain. And but that would be then sufficient to disprove arbitrarily long sidechain blocks or so.
So I guess the assumption here is that basically there's an efficient way to disprove like wrong inputs. So if we have like on the sidechain level, because as you say, they can a lot of data, the whatever sidechain essentially is connected or is plugged into this bitvm two-way peg would have to support on one hand a like line, and there has to be a way for this like line to really be compressed, like the proofs to be further compressed using knowledge proofs essentially, for this to be really like efficient on chain. If we think that let's assume it's like a Bitcoin fork, just use the same like proof of work. Let's merge mine coin, right? Just a copy of Bitcoin that's merge mined. Then probably essentially what you did with zero sync would be applicable here. So you try to kind of compress this.
Yeah, like there are two ways. Like one way is to use some kind of validity proof compression, and the other way is to just do very frequent updates. So for example, you would ask the prover after every sidechain block what they think is the latest block, or like the latest key block. Let's say like the latest block that is buried, I don't know, 200 blocks deep. And if they don't respond to that, then you challenge them.
But how would you challenge them? Sorry, I don't want to take this completely off implementation, so maybe I'll just keep my questions for another session. But the question is like, how do you challenge them? Right? How do you know? If you basically you just say, every block. Yeah, well, I guess you'd have to wait k blocks, right? So you'd be trailing kind of, because you need to somehow assume like, oh, we there's like this k parameter.
Yeah, but it wouldn't be necessary to wait for K blocks. You would just have some block that is already K deep, and then when another block comes in, then you have another block that is K deep, right? Like,
yeah, exactly. So you just have this, exactly. So it's not like live, I think, because maybe it was mentioned. So it's not live, but you basically have like, you challenge like 20 blocks in the past. So it's always kind of delayed.
You would challenge every block to reduce the amount of data that you would have to publish on chain in the worst case, because makes sense. But it's not like, it's not like on the sidechain. In this minute we mine block 10,000. It's not like you challenge him on. You ask him about block 10,000. You ask him about block 10,000 minus K, and K is like this parameter that will allow us to determine whether. So it's like. Exactly. So there's always like this delay, but it's just like for UX, right? It doesn't really affect this in any other case. Okay. Yeah.
And then essentially, as long as there's cable, you would just assume that they cannot be more than like a fork of deeper than K. And if he says, "Oh, this," then it's easy, right? So if he reveals the wrong block, the question is like, how do you punish him, right? So that's the question. Like, how do you really punish him for, like, how do you just assume like.
Yeah. I mean, if
so you need to
somehow, right? Like then.
Yeah, you need to figure out how he gets. So basically, you can't just say you're wrong. I have like result A, you have result B. You would essentially, according to bitvm logic, right? You have to then say, well, okay, prove to like I have to force you to somehow execute. Show me how you ended up with this block, and like somewhere you will have faked it, right? Yeah.
Yeah.
I have to basically find the invalid transaction or whatever you put into that block that made it different where you ended up. You basically have to find the fork points. Like the same way that FlyClimb basically does this with this interactive, like, or non-interactive proof. Actually, couldn't you use, if the sidechain supports FlyClimb, it could be made much more efficient, right? Or NepoPows, basically, where you can generate a non-interactive proof. So it's just a more efficient way, right? So it would be, but definitely make it cheaper. So if you're building a sidechain, then you should make sure to support FlyClimb basically and have the Merkle Mountain ranges in the blocks, so that if you want to support bitvm, it would be cheaper. But it will still be too expensive to really post it on chain, right?
Yeah.
Because you might find the block that you need to challenge, but within that block you need to produce a proof that the transition from the previous block was valid and not invalid.
Yeah.
So essentially, this doesn't work without a zero-knowledge proof proving state transitions between the two blocks, right?
It's quite interesting. Maybe you don't need that, because if you just have some way to agree on the latest state of the chain, then all the data that led to that state can be written into the bitvm memory, and you have 4 gigabytes of memory that you can write in there. And if you know the correct state, then you would know what you would have to write into the memory to arrive at that state. And if your counterparty does not arrive at that state, then there must be something wrong in the memory that they committed to. So I think there are ways to get around that limitation, that you don't have to.
You really? I mean, I guess the question is like, could you not so if you're sorry, and please interrupt me if we're going too far away from the actual code review, because I know this is a code review session.
A few more. It should be a question of the others. Like, what do you guys think? Is this interesting for you, or do you think we are going too deep into nitty-gritty here that is not clear to you guys?
This is interesting for me.
Okay, cool.
I guess I was just wondering, so the assumption of the two-way peggers, of the live clients, right, is, okay, you cannot produce more blocks than K deep. You cannot produce more than K blocks that have valid proof of work.
Yep.
So the problem, of course, is I could, right? Like, I could go back and, like, and the thing is, so in theory, of course, even on Bitcoin, I could start today. I could buy hash rate. It might take me a year, but I will just, mine K blocks in a row, like even with like 1% of hash rate. But I will be so far behind the main chain that so essentially by always following the tip until basically So as a verifier, I know what the tip is, I know what the block height is, right? So I can prove to you by revealing a few blocks, like especially if we use something like fly client. So it's not linear, but it's polylogarithmic. I can show that, hey, there's like a certain amount of blocks in this chain that all have valid proof of work. That's kind of the idea, right? So otherwise you'd find it. So because like the probability is very low that you basically challenge me and I've been able to reveal like the block that you basically, that because I can fight. That the idea is of these things, like if like clients, you can't fake the proof of work at least. So either you show all of them or you show like a logarithmic number. But by running essentially a binary search over it, like it's very, just the same way that you do it here, it's very unlikely for me to, like, it's nearly impossible for me to hide like an invalid block that I would have produced. Mm-hmm. So basically, if let's say you kind of have two parameters, right? You assume that nobody can produce a chain of longer than K. And then basically you would also say, well, and, like, I think it's just the freshness. You need to make sure that like all these things are fresh. So if you just assume that nobody can use bitvm to execute something that is like more than, I don't know, 2K blocks deep or I don't know, 100 blocks, you know what I mean, right? So if it's not like from 2 years ago, then you're kind of then proving, then basically your assumption is like, then basically I guess if the attacker, you kind of just challenge the attacker on the proof of work even. You don't even have to go into the transaction validation. You just challenge the attacker on the proof of work. So you just say, well, you should not be able to produce this, right? Because if you are, then it breaks, because then you're probably able to fork the sidechain, and then the sidechain, then you're probably right. So I don't think you really need to. I mean, maybe I'm completely wrong here, but maybe you don't even need the zero-knowledge proofs. You don't need to prove validity of a state transition between two blocks in the sidechain. You just kind of need to prove that there is no way for you as an attacker to have produced, that there is no way that you actually have a chain that is valid and that is kind of more longer than K blocks. Like the fork point between your chain and my chain is deeper than K, and this cannot be possible. So if you claim that you have this, so you're obviously claiming that your chain at block height 100,000 is the same is different to mine. This means that somewhere you lied, and I just need to find where you actually have the wrong proof of work. Speaking purely of like Bitcoin proof of work chain. So then I just challenge you, and then you can run the same bisection protocol by telling me to like fly client basically. So then you force me to reveal hashes, where I just check the proof of work difficulty. And I know that you won't be able to do it because unless of course you have more, unless you manage to really fork it. And then you're right, because in all fairness, then I lost, because that means the sidechain actually should be following your chain and not mine.
Yeah.
Does that make, would that allow us to just do it without any kind of state validity proofs? Just purely on this, because it is a like client assumption, right, that we have here, like no fork deeper than K. If there's a fork deeper than K, then everything breaks.
Yeah, I'm just not sure how many blocks you have to reveal in the worst case. Like,
it's not. It's logarithmic.
No,
fully logarithmic with fly client actually, but it gets very close. The problem is like so it does binary search essentially, right?
You reveal all of them on chain, and it works. Yeah. Then there is no problem. If you just use something like fly client, and then everybody, like, or at least the prover, they commit to logarithmically many hashes in the main chain, then there is no problem. Yeah,
I think it's like cost-wise it will be around the same, but essentially, but then you don't need to go into like the interesting bit. If I'm challenging you, like this is the first thing I'm going to challenge you, right? It's like, do we agree on the block height of the sidechain? Because if we don't, like I don't even care how you ran the execution of the redemption request of the peg out. I just challenge you on this, and then it's the same log number of like back and forth, right? I tell you, okay, reveal me your block. Like it's a bisection protocol. It's a binary search. It's different to what you have in bitvm on the instruction level, but it's just, okay, show me your block at. I'm trying to find the fork point basically. I'm trying to find where you lied, and then that allows me then basically at some point you will reveal something that definitely has not insufficient difficulty. and then I'll be able to verify that, because I guess.
I'm not sure, because I totally see how you find in logarithmically many steps the fork point, though after I found the fork point, I'm not sure yet how to prove that this is not a longer chain than my chain without revealing linearly many headers.
I think we can use the like verifier can challenge by giving a fork that is k deep by setting some, like revealing some pre-images from the memory, and then prover needs to state that its prover's inputs have more work than the verifier's inputs.
I need to read up again on Flycoin and the Merkle boundary ranges, or Nipopause for that matter, right? But essentially, the assumption is obviously that once I find the fork point, there is like I don't need linear amounts. Like honestly, I need to read up. I'll follow up, like, because I think the outcome of this is just like in a light client. I want to know, like, you're showing me 2 chains, and I want to know if you produced fake work. So the whole idea is that there is something in there. I'm just honestly, I need to reread it, and but essentially that's the assumption is that you won't be able to prove to me that you have a chain of length n with overwhelming probability, like having to reveal a block that does not have insufficient proof of work, because the assumption is like you can't have all of the, like, I just basically try to find one of the, like, the assumption is out of these k blocks, like, sorry, not k, like k is like the parameter, right? But let's say there's a number n that is lower than k. So let's say we assume no fork deeper than 50 blocks, and you basically say, well, you tried to do that. So I know that, okay, there's no way that you have more than 50 valid blocks, right, in your fork of where you claim it's 100 blocks deep, because I assume that's just not possible. And then I'm just trying to find one where you fake the proof of work to kind of get ahead of the main chain, because I assume that you can't, because you don't control the majority of the hash rate. And when I find this one, that's it, that's proof. The moment I hit, so I'm trying to find basically, and this is very high level, it's well described in the paper, but I just am poking around and trying to efficiently find where you lied. And the idea is I guess the fork point is where you should have lied. But I mean, that's wrong. It's not my description here is incorrect. But the idea is at some point I will find that you lied. And then I will know that you'll have to reveal a block that does not has insufficient proof of work. And then you lose.
Yeah, by the way, I think it's actually easier than I thought, because it will not be necessarily it will not be necessary to reveal the entire chain proof as bit commitments. I think it would be enough to just inscribe it into the main chain somehow. And
you just need the hash, that makes it. I just care about the hash, because obviously the hash gives me, I can verify if it has enough proof of work.
No, the hash is not enough. Like for example, in the case of a fly client, you would have to give me this compressed chain. Like you would have to give me logarithmically many block headers.
Yeah, for the non-interactive proof, right? But we're doing this interactively. But we're doing this.
You can do it essentially non-interactively, because if you had a chain of like 1 million headers and logarithm of 1 million times 32 bytes is just less than 700 bytes. And that's nothing. That's way more compact than, for example, a U32 commitment that we are currently using. So there is no problem to write a chain proof, a fly client like chain proof into the main chain. It is quite cheap in comparison to what we are already doing. So there is no problem about that at all. It's much easier than I thought.
So basically, then we just say, as if the sidechain has essentially the bottleneck here becomes like, how efficient can I prove the longest chain on the sidechain? If it's linear SPD, then there's a problem. Then you need to compress using something like ZeroSync, which works, right? I guess.
Yeah.
But then the complexity is actually, verifying that proof in bitvm. If it works out of the box, great. I'm not sure if it's. But if that's easy, then okay, perfect. And then the other alternative is if you have a more efficient way, it might be cheaper than to just say, okay, push this non-interactive proof like fly client, and then I'll know that whether you're lying or not.
Yeah.
Right. So basically, then the first step, the first step would be, okay, I disagree with you on the chain, and I force you to push this non-interactive proof, and whether that is like a compressed linear like client but compressed using like a zero knowledge proof, or if it's like this like client logarithmic set essentially of headers and hashes. And based on that, like if I'm wrong, obviously you win and you slash my collateral as a verifier. But if I'm right, which is the assumption, then it's over. And we don't even get to the bit like bisection protocol in the instruction level.
Yeah. And
cost-wise, it's probably the same as like the worst case scenario of bitvm. We're really cheaper. So it's not like it would cause a cost explosion if we go down that route.
Yeah.
I guess I wonder if there is. So the thing is about. So the thing is about if it doesn't have fly client, but it has like an SPV, then like if it's merge mined, but it doesn't have fly client at Bitcoin, right? Then essentially you don't have a way to. There's no prover for this in zero knowledge. Let's say for some reason, I don't know, non-pair, just whatever reason, right? Then you could just still run an interactive game, right? You could run fly client, but interactively.
Yeah, of course, yeah.
And then the cost overhead would be again logarithmic. So based on how many blocks deep, and you could obviously limit that, because if you say, okay, we will update this chain height every 1,000 blocks, then the maximum cost of this challenge response is known up front.
Yeah, it would become probably more expensive though, because you would need to express things in bit commitments, and that is usually very expensive. So I think it would be way cheaper to just do it non-interactively and ask the prover to just.
Oh yeah, 100%. I was just thinking, well, what if we don't have something like fly client and there is no zero knowledge proof basically that I can generate?
Yeah.
Like purely practical from theory perspective, yes, but in practice, what if I don't have that? Do I need to wait until somebody implements like a ZK like client for my chain, or can I just do this interactively? And then it just becomes more expensive.
I see your point. Yeah.
And then basically we'll say we'll update the chains every, like, I don't know, epoch, and the epoch is whatever, 100 blocks, 1,000 blocks every day or whatever. And then the cost is kind of capped. So if the prover any day has to, like, we do this every day, we catch up. And if you're lying, then I know the maximum cost of challenging you is predefined essentially. And you can time that. Like, the idea is that you know, if you skip a challenge, then you're out. Like if you skip one of these updates. So I don't update every block maybe, but like, we can also do every block in fairness. It's anyway off chain unless I challenge you.
But in general, I think it is a way better approach to start with a sidechain that is suited for being proven in the bitvm.
Oh yeah, 100%. I mean, sure. Yeah, absolutely. I was just thinking, okay, yeah. I was thinking if you want to connect this to Ethereum, what do you do? Because right now that is definitely more complex.
Yeah, definitely.
Anyway,
but I think they are
working on stuff. Yeah.
No? They are working on chain state proofs, and I think header state proof that already exists even in Ethereum.
I'm not up to speed whether they have enough. I just know that the problem with their actual lifetime model right now is that they have this vulnerability with the sync committee being able to sign invalid state, like they can sign invalid messages as long as you sign one honest, because they're not slashed. So you need something on top. This has nothing to do with actual bitvm. It's just a vulnerability in Ethereum, which whether it was done on purpose or not, like clients in Ethereum are not super secure yet. So you need anyway like a multi-sig or something on top. So, but that has nothing like, so anyway, like even if, basically you need like that plus a multisig to sign off that the sync committee was actually not signing invalid messages or something like that. Anyway, sorry, this is
Yeah,
getting completely out of
some kind of sidechain proof. I think you need some kind of state proof, at least something like a fly client or so. Otherwise, it just, I mean, you can do it. You can always do it non-interactively with just increasing the number of rounds in the worst case. Yeah, that is always an option, but I don't think it will be very practical because you actually want to reduce the number of rounds because they are the most expensive thing. Because yeah, it's the worst case time that you have to wait until you get paid. If you're honest, like if you're honest, you will always make a profit from getting challenged. Like from if your counterparty lies, then they will have to pay your fees at the end, but you will have to put up all the money up front. And yeah, that cost is the higher, the longer it takes in the worst case. So you want to reduce the number of transactions, and that's why I'm not a fan of this interactivity idea. I mean, of course, it will always solve the problem of Ethereum not having light clients, but it's costly. It costs lots of capital costs.
Okay, makes sense. Cool. Thank you so much.
Yeah, much.
Okay, cool. So let's wrap it up now. Yeah, we'll keep working on it, and we'll try to also come up with a couple more diagrams and stuff to explain better what we are actually doing here. And yeah, I guess we will do something like that also maybe next weekend or weekend in 2 weeks. I don't know. I guess that's Christmas. But yeah, we'll do it soon again because I think it's very valuable to yeah, get you guys feedback and yeah, see like get feedback if we are still on track or not. Yeah. So yeah, thanks for attending, and hopefully see you next time again.
Yeah, thanks, Robin.
Thanks. Happy Sunday.
Happy Sunday. Bye.
Warte, wie ist das Recording jetzt?
Gute Frage.